Assistant Professor of Anatomy at the University of Massachusetts Medical School. And in this recording series, I'm going to be focusing on the joints of the upper limb. The bones involved in these joints were discussed in an earlier recording series, and I would definitely make sure you watch that first. As you can see, there are a number of joints in the upper limb skeleton where the bones come together. It is that synchronized interplay between all of these joints that allows for the characteristic mobility of the limb and hand. All of the joints of the upper limb are synovial joints, meaning that they have a fluid-filled sac filled with synovium, which is actually Latin for egg, because basically it looks and feels exactly like egg white. Don't forget to watch our full body overview recordings to get a review of the different joint types. So, let's get started. In this recording, we're going to be discussing the joints of the pectoral girdle, specifically the sternoclavicular and acromioclavicular joints. Movements of the shoulder or pectoral girdle involve the usually simultaneous movement of three joints, and these are the sternoclavicular joint, the acromioclavicular joint, and the glenohumeral joint. Affect the functions of any one of these joints and it will impair movements of the whole pectoral girdle. We will be covering the glenohumeral joint in the next recording. In this recording, we'll be focusing on the sternoclavicular joint, or SC joint, and the acromioclavicular joint, or AC joint. So the sternoclavicular joint is the connection between the sternal end of the clavicle, here, and the manubrium. This is a pretty amazing joint because this tiny little area right here is the only point of bony articulation between the entire upper limb and the axial skeleton. It can be easily palpated or felt on yourself because when we look at it here from a lateral angle, we can see that the sternal end of the clavicle sits superiorly and anteriorly to the manubrium, meaning it sticks out more. The sternoclavicular joint is a type of saddle joint, but because there is so little actual surface area of bony articulation, it has a range of movement more like a ball and socket joint. So let's have a look at that now by swapping over and activating our supraspinatus muscle, the motion of which is abduction of the shoulder. If we hide all of our other muscles and we focus here on our sternoclavicular joint, you can see how this huge range of motion occurs. Obviously, being the only bony attachment for the upper limb, the SC joint is very strong, but it's also incredibly mobile, and this is possible because of its strong supporting ligaments. In fact, these ligaments are so strong that any forces that travel up the upper limb are actually more likely to fracture the clavicle than cause it to dislocate from this joint. So let's return now to our joints and look at our second joint, the acromioclavicular joint, or AC joint. This is where the acromial end of the clavicle and the acromion process of the scapula come together. The AC joint is what's called a plane joint. That's Plane. And you can actually feel this on yourself about an inch in from the point of your shoulder. So if we return to our supraspinatus muscle and look at its abduction motion, and we fade out all of the other muscles so we can actually see the joint as it's moving. And we're looking straight down now onto the point of the shoulder, and we can see this rotating movement of the AC joint. And if we look posteriorly, you can see that acromion process rocking even better. And that's the first two joints of the pectoral girdle. In this recording, we're going to cover the third and last of the joints of the pectoral girdle, the glenohumeral joint. What most people think of the shoulder is actually, anatomically, this glenohumeral joint, which is the site of articulation between the glenoid fossa of the scapula and the head of the humerus. The glenohumeral joint is what's called a multi-axial ball and socket joint. We've seen a few ball and socket joints already, but what this means is it has a wide range of movement, and in fact, the glenohumeral joint is the most mobile joint in the human body. But unfortunately, with all this wonderful mobility comes instability. You might remember from our previous bones recordings that less than a third of the humeral head actually articulates with the very shallow glenoid fossa of the scapula, so it's rather ripe for dislocation. Now, that shallow socket, or glenoid fossa, is made a little wider and deeper by the addition of a ring of fibrocartilage called the glenoid labrum. And I find it helpful to remember that labrum is Latin for lip, so it's really like the lip on a bowl. The freedom of movement of the glenohumeral joint is mostly due to the laxity or looseness of its joint capsule, which you can see here, a sort of loose fibrous layer surrounding the glenohumeral joint. So let's have a look at that in action. If we put our muscles back on here and we rotate towards the posterior, and we look at the action of our teres major, we can see the really small articulation surface that is maintained and the wide range of motion as a part of adduction and abduction. We can also see the process of extension and hyperextension and see how little of the head of the humerus is actually in contact with the glenoid fossa. And we can see medial rotation by fading our muscles. And again, lots of movement, but very little contact between the joints. So let's return now to just our joints. The shoulder joint is muscle dependent in that it actually lacks strong ligaments. The whole lot is held in place by the rotator cuff muscles, which you'll learn about in another recording. The glenohumeral ligaments are really just a strengthening of the joint capsule in that they're an intrinsic ligament. They're actually part of the fibrous layer of the joint capsule. They're called ligaments because there's 3 fibrous bands, but they're evident only on the internal surface of the joint capsule. The joint capsule also has an opening here, and this is for the tendon of the long head of the biceps brachii, which actually passes into the joint cavity. The weak joint capsule is protected by a structure called the coracoacromial arch. This consists of the acromion of the scapula here, the coracoid process of the scapula, and spanning between them, the coracoacromial ligament. And so that's the glenohumeral joint, the most mobile joint in the whole human body. Why not give it a stretch now before moving on to our next recording, looking at the elbow joint. The elbow joint. The elbow joint is one of those joints that everyone knows where it is. In fact, if you're a bit uncoordinated like me, it's that one you bash all of the time. But actually, the elbow joint is 2 joints, the first of which is the humeroradial joint, the connection between the humerus and the radius. And the more important of the 2, the humeroulnar joint, the site of articulation between the humerus and the ulna. In previous recordings, we've talked a lot about the parts of the humerus, the cylindrical trochlea and the rounded capitulum, as well as the radius and the ulna. The humeroulnar joint can be found about 3/4 of an inch below the epicondyles of the humerus. That's those stichiati bits on the side. And it's a synovial joint of the hinge variety. It has a fibrous layer joint capsule that surrounds it, seen here. and it holds in all of that wonderful synovial liquid lubricant. But the joint capsule is relatively weak, particularly anteriorly and posteriorly. And so it relies on collateral ligaments on either side of it to give it strength and support. These two ligaments are called the medial ulnar ligament and the lateral radial collateral ligaments. These are broken up into further terms, but don't worry, you don't need to know more at your level. Now, the collateral ligaments themselves are strong bands that aren't actually separate structures per se, but are thickenings of the fibrous joint capsule. The lateral radial collateral ligament is a fan-like structure, seen here. And its fibers blend distally with this structure here called the annular ligament of the radius, which we'll be talking a lot more about in the next recording. The medial ulnar collateral ligament is more triangular, and you can see all of these structures are a part of it. It extends from the medial epicondyle of the humerus to the coronoid process and olecranon process of the ulna. The elbow joint is a complicated one, I'm not going to lie. There is a total of 17 muscles that cross the elbow into the forearm and hand, most of which have some potential to affect elbow movement, or in turn, their actions are affected by the position of the elbow joint. But don't worry, it's not as complicated as it seems. To simplify it, just think of the hinge on a door. It can only do two things. It can open and close, and all the elbow joint does is flex and extend. The flexion part is limited by the coronoid process of the ulna, while the extension motion is limited by the olecranon process. So let's see that in action by adding our muscles back on here and focusing specifically on the action of our brachioradialis, which is elbow flexion. And if we fade all of the other muscles associated with that, we can see here, and from the posterior, we can see how that olecranon process is limiting extension. And then as we travel towards the lateral side here, we can see how that coronoid process is limiting flexion. We can see the full range of extension and flexion through the elbow joint and how the joint functions as a hinge type of synovial joint. See, it is simple. And that's it. That's the joints of the elbow. Now, try not to bash it. In the last recording, we discussed the elbow joint and its relatively simple actions of flexion and extension. Now we'll be looking at the radioulnar joints. These are two joints you've likely never thought about, but they control your ability to move your forearm and therefore to hold on to things and, importantly, to get food to your mouth. Try doing that without being able to rotate your hand. It consists of two joints, a proximal radioulnar joint and a distal radioulnar joint. Connecting the radius and ulna along their lengths, we have this long fibrous sheath called the interosseous membrane, and this is vital for ensuring the proximal and distal radioulnar joints act together. So let's start with the proximal radioulnar joint. This is a pivot type of joint, and its sole purpose is to allow the head of the radius to move against the ulna. This is seen better here in just bones. The head of the radius articulates with the ulna here at what's called the radial notch. You can see that a little bit better from a posterolateral view here. Returning to our ligaments, we have an important structure here called the annular ligament. This is the key structure, really, for the movement of the proximal radioulnar joint because it encircles the bony surfaces in a collar, which is made a complete ring by the radial notch. And this is what allows that radial head to pivot. Let's just do a little recap of our movements here. The forearm can be in pronation, palm down, or supination, which is palm up. And I always remember supination because if you're in supination, you can hold a bowl of soup. When we look at those movements at the radioulnar joint, by putting our muscles back on and focusing on our pronator teres, whose action is, unsurprisingly, pronation, we can see that the pivoting head of the radius is traveling around inside that radial notch. And you can see how it would be held there by that annular ligament. Let's go back to our joints now and look at our distal radioulnar joint. This is also a pivot type of joint. And the rounded head of the ulna here articulates with the more triangular head of the radius, the distal end of the radius. So it's almost the exact opposite of what we saw in the proximal end. Now these structures are protected from one another by a triangular sort of L-shaped articular disc here. And we'll be talking a lot more about that in the next recording. So if we want to look at the movements of this distal joint, we can put our muscles back on and focus on our pronator quadratus, which is also a pronator. Don't you wish they were all named that helpfully? Now, when we activate that, we can see that during pronation of the forearm and hand, the distal end of the radius rotates towards and over the ulna. During supination, the radius uncrosses from the ulna, so the bones again become parallel. And you can really see here why we say the ulna is the stabilizing bone of the forearm, because during this process it's not actually moving. And that's it. That's the two radioulnar joints. In the last recording, we discussed the radioulnar joints. Now we'll be talking about the wrist joint. The wrist joint, or more accurately, the radiocarpal joint, is a condyloid joint. This just means that it's like a condyle in that it has an oval articular surface that fits into an elliptical cavity. The joint can be visualized as a line drawn between the styloid process of the radius and the styloid process of the ulna. Or, in surface anatomy, by the proximal wrist crease. The wrist itself is composed of 8 carpal bones that we've learned previously. As we have discussed previously, the ulna is not active in the wrist joint, but it instead is the articular disc of the distal radioulnar joint and the distal radius, which move against the proximal row of carpal bones, most prominently the scaphoid and the lunate. See, radiocarpal joint. The name gives it away. The pisiform here does not participate in the radiocarpal joint because it actually lies anteriorly and only articulates with the traquetrum. So far, we have seen some pretty simple movements from our joints of the upper limb, mostly because we've been looking at pivot and hinge joints, except for the shoulder, which is a pretty much do-anything-it-likes kind of joint. In the wrist, we'll see a lot more complicated movements because we see flexion and extension, abduction and adduction, or abduction and adduction, depending on your pronunciation, and circumduction. So let's break that down by putting our muscles back on for a moment and looking at extensor carpi ulnaris, which has a role in extension and hyperextension. If we look here, we can see neutral into extension and hyperextension, neutral and flexion, back to neutral and extension. The wrist can be flexed more than it can be extended, and this is because the styloid process of the ulna, which we can see here, limits extension. Now, abduction and adduction, which can also be called radial deviation and ulnar deviation. Here, we're looking at adduction. You just want to remember that adduction means you're adding back to the midline because in anatomical position, the hands are palm forward. Now, it can be called radial deviation and ulnar deviation, simply meaning that there is a deviation either to the radial or to the ulnar side. So here you can see we have ulnar deviation, which is adduction. To see abduction, we've got to return to our muscle groups and look at the actions of extensor carpi radialis longus, which has wrist abduction as one of its movements. Here we can see abduction is simply a movement towards the radial side. You have much more motion in your ulnar versus radial deviation. This simply means that you can move your hands towards your ulnar more. Try it on yourself. This is because radial deviation is limited by the styloid process of the radius right here. Circumduction of the wrist consists of the successive actions of flexion, adduction, extension, and abduction. Basically, if you draw a circle in midair right now and look at what your wrist does, it's doing flexion, abduction, extension, and adduction. And that's it. That's the wrist joint. In the previous recordings, we've covered the joints of the shoulder and arm. And now we'll be talking about the last joints of the upper limb, the joints of the hands. Fair warning, these joints have some absurdly long names, but don't worry because we can use acronyms, and more importantly, their names describe exactly which bones are involved in the joint, and trust me, that's very helpful. The joints in the hand are numbered from lateral to medial, correlating to the numbers of the digits, with 1 for the thumb and 5 for the pinky. In the same way that we learned in an earlier recording to say the first metacarpal, it has a first metacarpophalangeal joint. See, big word, I warned you. But don't worry, we just call that the MCP joint. Let's look at the first of our major joints, the carpo-metacarpo joint, or CMC. These are saddle joints, and they're located between the carpal and the base of their opposing metacarpal. The CMC joints are highly mobile, allowing for flexion and extension, abduction and adduction, or circumduction, as well as a small amount of rotation. But the key thing about this joint is that it is vital to the opposition of the thumb. And we can see that if we add our muscles back on and we look at the actions of opponens pollicis, which is, of course, opposition. This is what allows you to touch your thumb to the pads of your fingers. Opposition is vital for grasping. You think about how you hold a pen. If we return now to our joints, we can look at the MCP joint, or metacarpophalangeal joints, which are located between each metacarpal bone of the hand and its associated proximal phalanx of the digit. The MCP joints are condyloid, moving only in two planes, the well-known flexion and extension, as well as abduction and adduction. These are the joints you know of as your knuckles. The last joints are the interphalangeal joints, and these are a type of hinge joint, and they're located where the heads of the phalanges articulate with the bases of the next distal phalange. Only flexion and extension occurs at IP joints, and we anatomists name these joints for where they are. So the only IP joint proper is located in the first digit because, as you may remember, the thumb only has two phalanges. The proximal interphalangeal joint, or PIP, occurs at the joint of the proximal and middle phalanx of digits 2 through 5. while the DIP, or distal interphalangeal joint, is located between the middle and distal phalanges of digits 2 through 5 again. And we can see all of those in action by adding our muscles on and looking at our flexor digitorum profundus, whose actions include flexion and extension of our MCP joint, as seen here, and flexion and extension of our interphalangeal joints, which we can see as the fingers curl up. And that's it. You've learned all the joints of the upper limb. Congratulations!